All right, let's jump right into this explainer. Today, we're unpacking something pretty mind-blowing. We're looking at how a single profound geometric realization actually solves one of the oldest mysteries in both computation and physics. We're going to break down this incredible framework, really zeroing in on the mathematics behind something called the silver partition invariant and the Turing cell. So, if you've ever found yourself wondering about the absolute fundamental limits of reality and computation, well, this is going to be a really fun ride. Let's get into it. So, we have to start with a paradox that seems pretty much impossible to solve. The question is, how exactly do you force an infinite process to physically stop? You see, for decades, scientists have really struggled with the fact that classical math relies entirely on continuous fields. And that means whether you're trying to build a complex computational model or just map the trajectory of a photon, using continuous space implies your equations can, theoretically, just run forever. They just keep spitting out an endless string of decimals. So how do you logically and physically build a solid floor for the math to actually stand on? Well, to understand the solution, we first have to validate the problem, which stems from this concept called xenodrift. You might remember Zeno's ancient paradox of Achilles chasing the tortoise, right? The idea that if you constantly have the distance between them, Achilles never actually catches up. In classical math, space is infinitely divisible. And because of that, an algorithm can literally fall into this zero-dimensional black hole, just endlessly dividing into smaller and smaller fractions without ever hitting a final destination. The source materials we're looking at describe this continuous space as undifferentiated gunk. It's like infinitely stretching dough, a place where algorithms basically just hallucinate their way down a never-ending rabbit hole. Okay, so the crucial turning point here is contrasting that bottomless mathematical dough against a totally new, structurally sound framework. It's a shift from point atom space to discrete tiles. Just think about the difference. On one hand, you have the legacy point atom space. These are essentially zero-dimensional ghost points that offer absolutely zero resistance, which is exactly what allows that infinite division. But then you have discrete tiles. Think of these a lot like rigid Lego bricks. The fundamental building blocks aren't abstract empty dots anymore. They are actual physical surface boundaries with a strictly finite area. By shifting to this bit-perfect grid, we completely bypass that whole endless fractional fracture altogether. Think of this new discrete tile metaphorically as a rigid biological cell wall. It's a bounded mathematical container that explicitly prevents that endless division we were just talking about. This is exactly what the research identifies as the Turing cell. Alan Turing himself envisioned this kind of discrete, rule-governed morphogenesis. By completely abandoning the empty point and adopting this tile as our basic metabolic unit, we establish the physical boundary that is absolutely required to guarantee the math stops. Instead of an algorithm falling down an infinite well, it lands securely in a stationary, highly functional container. Now, what's really fascinating here is how the mechanics of this cell wall actually operate. It all comes down to the unit constant, which is called d0. The overall geometric shape is perfectly composed of its own nested substates. Specifically, it's made up of two primary sublenses, which we'll call D1, and a single secondary refinement, D2. It forms this perfectly sealed geometric boundary. And this isn't just an interesting pattern. This is the literal physical foundation for deterministic computation. It means the system updates via discrete, whole steps rather than getting lost in a messy cascade of fractions. And that perfectly sealed geometry leads us right into a magical algebraic reveal, known as Theorem 1, the silver partition invariant. The geometry translates flawlessly into a solved quadratic equation. So step 1 is that physical partition we just established. The unit cell, D0, equals 2 D1s plus 1 D2. Then, in step 2, by substituting the resolution scales and normalizing D0 to 1, we get this incredibly elegant formula. 1 equals 2d plus d squared. And finally, for step 3, when you actually algebraically solve for d, you get the exact equation for the unique positive root, d equals the square root of 2 minus 1. Resolving that quadratic lands us exactly on 0.414214, which is the unique positive root of the silver ratio. Guys, this is monumental. The 1-to-1 silver cell is the only integer ratio geometry that perfectly constructs this mathematical horizon without any approximation error whatsoever. So what does this mean in plain English? It means we get a totally flawless state machine. It doesn't stretch into an infinite line, and it doesn't collapse into a dense point. It achieves a pristine equilibrium. Amazingly, It's the exact same geometric balance that has historically stabilized everything, from ancient Japanese pagodas right down to the standard piece of A4 paper sitting on your desk. And this brilliant ratio is what physically corks the infinite fraction. Because our Turing cell has a finite area that is defined by the silver ratio, it creates a completely rigid boundary. It effectively transitions computation away from those endless algorithmic hallucinations and forces a finite halting step. In fact, the source materials literally refer to this physical boundary as the cork. So instead of spiraling down into an infinitesimal ghost point, the resolution remainder hits the noise floor and physically bottoms out. It securely captures the state, acting like a literal cork in a mathematical drain. Now, when you scale this outward from a single cell to a much broader grid, you can prove how this bit-perfect unit scales exponentially to form a completely stable horizon. Take the diamond tile spiral, for instance. You'll find that perfect square values land with absolute precision along the cardinal white tiles. And when it comes to angular rotation, instead of hitting a wall where you suddenly need a bunch of messy, irrational approximations for angles, this lattice achieves rotation through native, discrete, whole number steps. It's incredibly elegant. The real-world implications of replacing those old ghost points with this rational boundary are frankly staggering. By locking in deterministic halting at the unit shard level, we establish a strict energy floor. And to actually prove this, researchers ran a 1,000-step simulation pitting this geometric lattice against legacy continuous systems like TurboQuant. Unsurprisingly, the legacy systems eventually drifted into error. But this discrete lattice, it maintained a cumulative error of exactly 0.00000. That zero precision drift is the ultimate empirical proof that building on bit-perfect geometry truly works at scale. So, we've seen how the silver partition invariant and the Turing cell structurally lock down deterministic halting, effectively solving a math problem that has literally haunted computer science for nearly a century. And it leaves us with this fascinating concluding thought. If the continuous infinitesimal point is truly just an illusion, just a ghost of legacy calculus, how many other laws of physics, economics, and information theory are just waiting to be completely rewritten by the geometry of the cell? When you build upon a solid foundation instead of an empty void, the possibilities are strictly bounded yet infinitely profound. Thanks so much for joining me on this explainer.